Hi everyone, my name is Abhishek Gupta and I'm here to talk about our work on reset-free reinforcement learning via multitask learning. This is joint work with a number of collaborators at UC Berkeley. So the key question we ask in this work is how can we get robots to learn complex behaviors like pipe insertion or dexterous in-hand manipulation as shown here? We really want to be able to enable our robots to just be dropped into environments and be able to acquire these skills autonomously on their own. When we think about robots acquiring skills autonomously on their own, the paradigm that most often comes to mind is that of reinforcement learning. So the paradigm of reinforcement learning involves an agent interacting with the environment through trial and error in order to learn a policy that maximizes the notion of collective reward. So reinforcement learning is a really powerful paradigm for learning complex behaviors because it can learn behaviors without any pre-provided model of the world directly through trial and error. Now, this has been a really useful tool for learning complex behaviors in simulation. So you can learn complex behaviors with the dexterous manipulator like object relocation, in-hand repositioning, and even tasks like door opening. However, training agents in simulation requires considerable engineering to actually design the content, which is accurate for simulation, and also be able to transfer the simulated behavior into the real world. So simulation becomes quickly hard to scale as we go to more and more complex tasks. So what's a simple alternative that we could take? A simple thing we could do is try to directly train robotic learning agents in the real world. This is what we refer to as real world training. Now, when we consider reinforcement learning in the real world, it looks something like this. You try to interact with an object for in-hand manipulation, for instance, let's say here. But as you keep interacting with the object, it can fall out of the palm into the bottom of the arena, which becomes hard to recover from. If you're trying to learn directly in the real world can often enter these states which become hard to recover from. So this makes learning autonomously quite difficult. Now, one way we could try and deal with this is have a human in the loop, which comes in and resets the object back into the palm every time it falls out of the hand. But this goes against the whole spirit of autonomous learning. If a human is constantly required in order to keep babysitting the robot and putting objects back in the palm of the robot, this makes it hard to actually scale up autonomous learning to collect huge amounts of data without supervision. And in fact, many of our current real-world reinforcement learning setups actually require this kind of human intervention or instrumentation. So here we have some examples of learned behavior with reinforcement learning. But if you look at the training setup behind the scenes, we see that it requires pretty careful human intervention or specialized reset mechanisms like a servo motor which keeps closing the door after every attempt, or a funnel mechanism, an especially scripted arm that keeps putting the balls back in the hand for in-hand manipulation. This becomes quickly hard to scale, and what we need are algorithms that can learn without requiring these types of episodic resets. That's going to be our focus in today's paper. We're going to try and design algorithms for reset-free reinforcement learning or autonomous learning at scale without episodic resets. So let's look at this problem of learning without episodic resets, what we call reset-free reinforcement learning, in a little more detail. Now, in a typical reinforcement learning setup, you're going to assume that you can sample an initial state from an initial state distribution row. Then you can execute a policy in the environment to collect trajectories and maximize the sum of rewards in these trajectories. In a reset-free reinforcement learning setup, you don't actually have access to sampling and resetting from this initial state distribution, and instead, your initial state is completely determined by the trajectory that you executed right before. Therefore, you have an inherently non-stationary and difficult problem. But why is this problem even important? So reset-free reinforcement learning is important because it fundamentally limits data scaling if you require resets in the entire learning process. So any autonomous data collection technique is only as scalable as its weakest link. Even if you have a great method for inferring rewards from proprioceptive observations or trying to learn from high-dimensional camera images, if you still require a human constantly in the loop in order to provide these episodic resets, the scalability of the data collection pipeline is fundamentally limited. This suggests that we need algorithms for reset-free reinforcement learning. But why is this difficult? Now, reset-free reinforcement learning is challenging because the agent can get stuck in certain states for really long periods of time. So for instance, let's say we're trying to push this cup to a particular location. If the cup slips out of the palm, the agent can get stuck there for a really long period of time without interacting with the cup. What's even more nefarious is that if you actually succeed at performing the task, then the right thing to do is to do nothing at all. If you do nothing at all, then the agent fails to continue getting better at robustly performing the task because it's not collecting any novel data. Now, this is clearly evident in our task of dexterous in-hand manipulation when we consider how exploration proceeds. We can see that initially the object's in the hand trying to be repositioned, but it very quickly falls out of the hand. When it falls out of the hand, we can see that it will get stuck there for a really long period of time until the robot accidentally picked up the object, brought it back in the palm to keep practicing again. And so reset-free reinforcement learning can be quite challenging for these single tasks in isolation. So if we need algorithms for reset-free reinforcement learning, we need them to be able to set up their own practice problems. What do we mean by this? Let's consider, for example, a robot in a kitchen. If a robot in a kitchen is trying to put this kettle into the sink, let's say in the first episode, it tries to put the kettle into the sink. Right? Now, at the end of the first episode, let's say it's put the kettle in the sink, then it needs to figure out what it's going to do next. Now that the kettle is in the sink, where do I move the kettle to next so that I can practice appropriately and keep getting better at the task at hand? A number of prior approaches have tried to consider this problem in a little more detail. They typically try and tackle this problem in two different ways. The first class of methods, which we're going to refer to as a forward-backward controller, tries to tackle this as follows. It says that let's try and move the kettle into the sink, but also learn a controller which is going to take the kettle out of the sink and put it back onto the stove. So let's learn a backward controller, which is going to explicitly try and reset the kettle back onto the stove. The second class of methods, which we're going to call a perturbation controller, is something a little bit different. In the perturbation controller, we're going to try and consider moving the kettle into the sink, but instead of resetting back with the same fixed initial state, we're instead going to try and perturb the state as widely as possible. So once the kettle is in the sink, it's then going to try and pick up the kettle, put it on the counter, put it in the cabinet, put it on the floor, and so on. Therefore, perturb the state as much as possible. These algorithms have been successful in some settings, but they might not be successful in our complex dexterous manipulation settings. Why is that? Now, it's difficult to actually extend these to complex tasks because for the forward-backward controller, the exploration problem for learning a reset controller can often be quite challenging. So for instance, in the task that we considered earlier with dexterous manipulation, learning a backward controller involves learning how to pick up the object, flip it over, bring it back to a perfect position, all in a single controller, which can be quite challenging. On the other hand, a perturbation controller can often become hard to scale as you go to larger and larger state spaces because there becomes more and more elements to perturb. So this doesn't scale well with dimensionality of the state space and with confounding variables. So this suggests that we need a better solution. Now, one observation we make is that exploration and combinatorial explosion are largely a problem in the single task setting. When we consider solving a single task at a time, exploration can be quite challenging, and the number of elements in the state space can still blow up. However, we're not typically in the single task setting. We typically do want to solve multiple different tasks together. So for instance, let's say we're considering the robot in the kitchen again. We don't want to just put the kettle in the sink. We instead want to also solve the task of opening the cabinet, picking up the kettle, closing the cabinet, opening the fridge, picking up an object off the floor, and so on. Right, so we want to be typically solving all of these tasks together anyways. And the question really becomes, when we're solving all of these different tasks together, can reset-free reinforcement learning somehow be easier when you have multiple different tasks? The key idea we're going to leverage in this work is that when you're solving multiple different tasks together in a reset-free manner, some tasks can serve to provide resets for other tasks just by being learned naturally in sequence. So to understand what we mean by this, let's consider the same type of task that we had earlier. Let's say we're trying to move the kettle into the sink. And in the process of moving the kettle into the sink, let's say you drop the kettle on the floor. Now, just by learning the task of picking up the kettle and putting it on the counter, in sequence, you naturally automatically provide a reset for the task of putting the kettle into the sink. So just by appropriately sequencing tasks one after the other, we can put the environment into state for learning all of the tasks becomes easier. Right, so let's consider how this applies to a concrete instantiation. We specifically consider the dexterous manipulation task that we described earlier. More specifically, we have a 4-fingered robotic hand with 16 degrees of freedom and a 7-degree of freedom robotic arm, which is controlling this hand. And the goal here is to manipulate this 3-pronged object and do in-hand manipulation to orient it in a particular position and orientation. An example of a successful outcome is shown here on the right. Now, if this task was being solved in isolation, as we saw earlier, the reset-free reinforcement learning problem can be quite difficult. But instead, what we're going to try and do here is solve multiple different tasks together. So we might be trying to solve the task of recentering, picking up, in-hand flipping, and in-hand reorientation all together. The key here is some tasks can provide resets for other tasks naturally. So if we consider how the reset-free reinforcement learning process would work, let's consider an example run of the training process. We start by trying to lift up the object. And let's say this was unsuccessful. Then the object would fall back on the ground. Then we have to learn how to recenter it again. Let's say we learned how to recenter it now. We tried lifting it again, and this time it is successful. When it's successful, we can then start attempting the task of flipping up. Once we've tried flipping up, let's say it's successful, we can practice in-hand manipulation now. We practice a couple of iterations of in-hand manipulation till the object falls out of the palm, then we recenter it, lift it, and try it again. Right, so let's see how this actually looks empirically. We can see that initially the object's in the palm, but it quickly falls out of the palm and onto the arena. We start by trying to learn how to recenter the object. We spend a long period of time autonomously interacting with the environment, trying to reset the object to a certain position in the middle of the arena. Now, once we've learned how to recenter the object in the middle of the arena, this naturally provides resets for the task of lifting. If you've actually recentered the object every time it falls down, you bring it to the middle, you practice how to lift, and after around 30 hours, we're able to successfully lift up the object. Now, lifting starts to provide resets for the next task of flipping it over so that the palm is upright. So this, in around 40 hours, you can learn how to do flipping over, and this allows you to then practice the task of in-hand manipulation, which orients it in a particular angle and position. After 50 hours, we start to see some life in the in-hand manipulation task. After around 10 more hours of training, we can see that we successfully learn how to pick up the object and orient it in a particular angle and position. This involves fine-grained finger manipulation, and what's particularly impressive about this is we've trained it for around 65 hours without requiring any human intervention in the process. Most reinforcement learning systems that currently exist will only train for a few minutes or at most a few hours without requiring any human intervention, whereas the system we designed here can go up to several days without any human intervention. Now, the same type of results can also apply to different tasks. So for the task of pipe insertion, for instance, the goal is to pick up this pipe and insert it into this hose attachment as shown here to the left. An example of a successful outcome is indicated through this picture on the right. We can see that we want to learn multiple different tasks together, like recentering, picking up, insertion, and removal all together, which each task providing resets for other tasks in a network as we discussed earlier. Now, the resulting training process looks something like this. Now, we start with the object on the ground, then we learn how to recenter the object in the middle of the arena. We spend a long time trying to figure out how to recenter the object in the middle of the arena. We have successful behavior as shown here. Now, this starts to provide resets for the task of lifting. Once you're able to lift successfully, we can then start providing resets for the task of insertion. And after around 16 hours, you learn how to insert, and after insertion, this provides resets for the task of removal. We can then learn how to properly remove the object from the peg and then continue this process to keep getting better and better. After around 24 hours, the final behavior looks something like this. We're able to successfully pick up the object and then insert it correctly into the hose attachment on the left. Another viewpoint of the final behavior looks something like this. We're able to reposition the object, pick it up, insert it into the particular position, and successfully keep repeating this, getting better and better as we keep training. Now, these types of results also extend to several different tasks in simulation. We can consider the task of light bulb insertion and basketball dunking, where the goal is to pick up this light bulb and insert it into a particular position in the lamp. And basketball dunking, where the goal is to pick up this basketball and dunk it into this hoop. These are trained autonomously by leveraging multiple different tasks as shown here by the color bar on the bottom. These results also extend to quantitative results, where we see we do significantly better than a reset controller or a perturbation controller or naive off-policy reinforcement learning, as we discussed earlier. So the key takeaways from this work is that reset-free reinforcement learning can be quite challenging in the single task setting. Learning multiple different tasks together can, however, make this problem a lot easier because some tasks can provide resets for others. By doing this type of paradigm, we're able to learn complex dexterous manipulation behaviors with minimal amounts of human involvement and really scale up autonomous learning far beyond what was previously possible. Thank you.